You have been doing. If you did not get a chance to attend one of the supplemental instructions, please do bring your activity 36 up and drop it off with Lepara. That's what people are teaching. Very nice. I think we had fewer numbers at supplemental instructions last week, maybe 20 to 25 people were able to go. And this was an activity I really did want you guys to complete because we're going to be starting talking about kinetics today, and you're doing it in the lab this week. So it is going to be important to make sure that you're getting up to speed. If you have forgotten or somehow were unable to complete it before today, do it, turn it, complete it, give it to me before the exam on Wednesday, and there'll be a point deduction, but you'll still get some credit. It'll still be valuable to do. All right. Any questions about activity 36? Hopefully you brought activity 37 with you, because I do not have 55 copies of activity 37, and we're going to be working on that some today. Hopefully. All right, let's go ahead and start. I did go ahead and look through the people who turned in. I looked through the activity, the chem activity on fracturing that people turned in chem activity 10, which was on heat curves. And I saw a couple of common misconceptions that people had. So I wanted to try to take the first couple minutes to address those because our exam number 1 is on Wednesday evening. And if you don't have your name pens out, if you could please bring those. I still don't know everyone's name, unfortunately. I'm trying, but if you could put those out, that'd be great. All right, and also for other people in class, not everyone knows each other's names, even if I do. Go ahead and answer this question. Check with your neighbor. Do you concur? We have 42 responses. A couple more seconds. All right. Interestingly, we had some people shift their votes one way, and then the shift came back the other way. So I am going to show you guys the data. We have a 2-to-1 response. 2/3 of people say that no, this is not a polar molecule. 1/3 of people say that yes, this is a polar molecule. Can I have someone who answered the majority answer describe why you think that this is a non-polar molecule? Angel?
There's not very much polarity between hydrogen and carbon, and then from the chlorines, they're moving towards the carbon, so they cancel out.
Okay, so which's more electronegative, carbon or chlorine? Okay, so everything tends, most electronegative element that bonds is chlorine. Everything up in this direction becomes more electronegative. So chlorine is more electronegative than carbon. So I would have even gone one step earlier in your discussion and say that, are there any polar bonds? If the answer is no, done. Don't need to do anything else. What is the big misconception that 2/3 of the class had on this problem? Josh?
You think the shape kind of messes people up?
What about the shape?
Looks dead even, so people are like, oh yeah, what's up?
Totally opposite directions. Cancels out. Wrong. What is the shape around that central carbon? It's got steric number 4 domains of electrons around it. That means it's tetrahedral. It has 3-dimensional space. It's not a piece of flat material stuck on a page, right? So 2 of those, you can look at it, it rotates around in space, right? But one of the ways you can do is the 2 chlorines come out towards you, the 2 hydrogens go away from you, and then they have more than 90 degrees space between each other, which gets less repulsion by the electrons. So this is true that this is a polar molecule. And this is a concern that 2/3 of the class forgot about first semester Gen Chem. So I do really want you guys thinking about what is the 3-dimensional representation of molecules. Lewis structures only get us so far. There are 2 dimensions. It's really hard to draw 3 dimensions for that. So those dipoles, actually, if they're both coming out in these directions, don't cancel each other out. And the center of the negative, partial negatives, is not on top of the center of the positives. If you go back to our chem activity 23, 22, 23, one of those. So make sure to go back and review those activities before the exam. Even if I know I didn't turn chem activity 22 back to you, you still have the PDF. Go back and look through that and make sure you can identify when there is polarity and when there's not. The reason that this came up is because this compound was one of the ones in the Pogel fracking activity. So go ahead and answer this question. Is this compound polar, true or false? Once you've submitted your own answer, then go ahead and check with people around you. A couple more seconds. All right, what do you think the response is? Is it going to be split again? So we're almost in agreement here. Where might the misconception be if we answer that, no, this is not a polar molecule? What misconception would be playing up there? Mohammed, do you want to share it clearly?
Sure. Because the OH is on each side, people might think they'll cancel each other out.
So if this is an accurate representation, you're going to say, well, I know there's a polar bond there and a polar bond there. Equal and opposite direction pull, cancels out. But once again, we're ignoring the fact that it's in 3 dimensions. Once we do that, we know that this is tetrahedral, this is tetrahedral. What about the oxygens? Are those tetrahedral or something else? So each of the oxygens should have 2 lone pairs. That OH should actually have a line between it if we want to draw everything out. But in organic chemistry, we simplify and we put OHs next to each other. So there's another bond there. That's tetrahedral too. So the OH is polar, the CO is polar. Those are at 109.5 degrees from each other. This is at 109.5 degrees from each other. So this molecule is very polar. Not quite as polar, like pound per pound compared to water, because water is only polar bonds. Here we have nonpolar, 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 nonpolar. So we do have some nonpolar bonds, but for the most part, that's a very polar molecule. And I saw a number of people when we had to identify that in the Pogel activity on fracking said that this is a nonpolar molecule. If you didn't get a chance to complete that activity, once again, all the supplemental instruction activities, if you don't do them for supplemental instruction, are really good study tools for the exams. So go ahead and look back at those and work through them if you have not yet already. Did I see a hand raised, Matt?
I was just questioning, so you said the electron pair geometry is tetrahedral, but the molecular one would be bent, right?
For
the
oxygen.
HOC.
Correct. Yeah. So it is a bent molecular geometry because it is tetrahedral electron pair geometry.
Okay.
Thanks for the clarification. All right, any questions? One other question from that was to draw water molecules interacting with I think it was with a peptide. So talk to your neighbor, what about this drawing might show a misconception? Okay. Can I hear from a new voice? Maybe if you talked to your group and found an idea, there's something that stuck out. Humphrey?
The H is bonded to a C.
Okay, there is an H going to a C. This is correct. How does that relate to this question?
Because hydrogen bonds have to be between an H and an N, an N over F.
Okay, so we have that. We have an H, and that's interacting with an O. So we're good.
Like the one that's inside of like the one on the bottom, it has to be N over F. Like they both have to be N over F.
So you're saying that this has to be a nitrogen, fluorine, or oxygen?
No, the one that the hydrogen is bonded to has to, yeah. That
Why? Why can that not be a carbon for this statement to actually work? What makes it special if that, what we're pointing at, is a nitrogen or oxygen? Ruby?
This here, for the hydrogen to nitrogen or oxygen bond will be polar, but that's not a polar bond for CH. So it doesn't have a dipole.
Great, so what Ruby's getting at is there's no dipole moment here. Because we have two things, like Angel said before, that are almost the same electronegativity. This is a non-polar bond. Remember, hydrogen bondings are a special, exaggerated case of dipole-dipole interactions. This is not even a dipole-dipole, so this cannot be an even stronger version of dipole-dipole. So here we do have dipoles that are pulling towards the center of oxygen, but we don't have any dipole, so the hydrogen in the red circle has no partial charge. Is there anyone in this molecule where we could have drawn a water molecule interacting with the O specifically? What's that, Logan?
There's two hydrogen and H2.
So if we have a water molecule drawn here, we could have that interact with one of the hydrogens that is electropositive. It does have a partial positive charge because it's attached to an oxygen or nitrogen. That's a really big distinction. So this is one of the biggest misconceptions when I ask students to visualize how water molecules help dissolve other compounds. This is not an appropriate interaction, especially if we're describing hydrogen bonding. This might be described as a dipole inducing a dipole, maybe, but there's no way that's even a dipole-dipole or the strongest of the dipole-dipoles. Do you think I'm going to ask you to draw something like this on the exam?
Yes.
Uh-huh. So if you're not comfortable with what we're talking about here, make sure to go back and look at the class, or that fracking activities one where we have some of that stuff. Post message discussion board, try to come find me, talk to tutors, talk to your TAs, talk to other people in this class. Make sure you're very confident in drawing interactions between two molecules that do classify as hydrogen bonding, specifically water with another molecule. All right, so in class today, I want us thinking about solubility at first. So let's look at another statement. And it builds off what we were just talking about. All right, closing out. You guys answered this pretty confidently. What trend do you notice with solubility and temperature of a solute, like sugar or table salt or other things? What do you guys notice happens? How does the temperature relate? Austin, how would you describe that relationship?
Solubility increases as the temperature increases.
Yeah, so if we want to have sugar in our coffee, if we want iced coffee, right, we're not going to put sugar in the iced coffee. We're going to put sugar in the warm coffee, dissolve it, and then cool it down. So the dissolving process gets much worse when it's colder. So I want us taking that and contrasting that with how gases dissolve, because some parts might be similar, some parts might be very different. So this kind of relates to Henry's law, some of the stuff that you guys have been doing in your homework. And I want to take our discussions of dissolving and applying that to what Tyler's super excited about, which is climate change, and how CO2 in the atmosphere dissolving the ocean is impacted by a number of things. What's that, Lynn?
I'm so excited about climate change.
All right, so there's a number of different factors. You guys have already seen a lot of these in the activities we've done in class and supplemental instruction: increasing global temperatures, increasing atmospheric CO2 concentrations. And so we're going to have that perspective, that lens, as we start talking about gases dissolving in solution. So let's take a similar scenario, thinking about how something dissolves in water, but now let's think about gas. So click in your own answer, then check with your neighbor. Close to 50-50 on this one. Find someone around you that answered differently and convince them why you're right.
Yeah, can we argue with ourselves?
If you change your mind, submit your new clicker. If you didn't change your mind, you don't need to touch it. We convinced 3 people. Good job, guys. All right. Would anyone who changed their mind, one of those 3 people, be willing to share the conversations you had? Maybe that helped you change your mind?
It's okay.
Savannah?
So my conversation with Lev was that when you open a carbonated beverage and you put it in the refrigerator, the carbonation normally lasts longer than it would if you just left it out on your counter. So I changed my answer from A to B.
Okay, so you said that increasing the temperature of solution decreases the solubility of gas because your own experience with soda. Great. Any other examples you guys have seen with that in your own lives? Have you ever tried putting a can of soda on a hot plate or like on the stove or something? Love, you've actually done that? What have you seen? It froths up and it boils up really, really quickly. Imagine if you did the opposite. You took a warm can of soda or other fizzy beverage and you put it into an ice bucket. Do you think it would just fizz over? You'd do the opposite, right? It would slow that down. So what we're talking about today is why it is that that happens, thinking about intermolecular forces and a number of different things. So if you look at concentration of carbon dioxide, talking about carbonation, right? How much does that dissolve in liquid over time? With temperature. So the solubility is measured here in grams per 100 mils of water. And what do you notice happens as you warm it up? Does it decrease just a little bit?
A lot.
It's pretty drastic, right? It goes from 0.35 on the scale at 0 degrees down to 0.05
Yes.
at 60 degrees. Colin?
My question was a second ago. So if you like shook up a can of soda and you put it in the freezer, is that a good way to get it, like keep it from spewing when you open it?
That would probably be a good way to slow all the molecules down. So what you're talking about is actually kinetic energy and disturbing a physical equilibrium between them. So a can of soda is not at equilibrium. We forced artificial conditions by compressing a whole bunch of CO2 into the liquid. So giving it a whole bunch of jarred up kinetic energy doesn't help with that. So if you cool it down, it does the opposite, right? It pulls it back. So yeah, but don't leave it in there too long. Or put it in a freezer that's not at minus 18 like a normal freezer. Put it like, I don't know. If you have a variable temperature freezer, do it at a variable temperature. Like all us chemists do, right? All right, so the big question is why. Here's a number of different molecules. So we have helium gas dissolving in water, carbon monoxide, oxygen, and methane. I want you to talk to your neighbor. Try to think about the logic behind why it is that an increase in temperature results in a decrease in solubility. Go ahead and take a minute. Formulate a phrase that you can share with the class between you and your neighbor.
That's what we were doing just
You got me nervous. I was putting it right one. It just popped up and
All right, I'd like to hear from a new group who's been discussing this. Why is it, do you think, we could describe the amount of gas that dissolves decreases as temperature goes up? New voices. New voices. Please. Echo.
I thought it was because whenever you have a gas that's in a liquid that's being heated up, the kinetic energy within the gas, like how the gas particles, I guess, kind of move, that they would kind of break free and become vaporized. So so the solubility would become, like the concentration would go down.
Okay, does anyone want to, I think we're on the right track, does anyone want to add to that with additional descriptors or concepts? Aaron?
We were talking about how if you increase the temperature of a solution, it increases the vapor pressure. So if you have that increase in vapor pressure, there's more vapors coming off the solution bouncing against gas particles in the air, which pushes them further away from the top of solution and keeps them from dissolving as quickly.
Okay, I can see where you're going there. So you could say that you'd actually, depends on if there's space for those gas molecules to move away, but it could kind of open some more space. So I think the big thing that I'm hearing from both of you is that you have an increase in molecular speed in the liquid when you warm up a sample. Let's think about intermolecular forces. Do you think gas molecules typically have very strong intermolecular forces with liquid solution with water, and why? There's a few examples here that you might be able to draw from. These molecules have very strong intermolecular forces with water. Do some of them. What kind of intermolecular forces is helium going to have with water? So, to answer this question, is there an ion in helium? Is there a dipole in helium? Is there any partial anything in helium? Okay, so it can only do London dispersion forces, and you can maybe have the dipole in water induce a dipole in helium. But for all intents and purposes, that's a relatively weak intermolecular force. What about carbon monoxide? Is that the same? Is there a dipole or an ion in carbon monoxide? Is there a dipole? Yes or no?
Yes.
Carbon and oxygen are different in electronegativity. There is a dipole. And it depends on what Lewis structure you draw. There are ions as well in that, but That's a bit more complicated than we're going to get into today. So there is more attraction here than there is for helium. O2, CH4, are there any dipoles in those molecules? Non-polar molecules. And what you find is that most gases are non-polar for the most part, at least with the ones that we're going to be looking at. So let's think about that. Relatively weak intermolecular forces because they don't have a lot of polarity. So as we increase the kinetic speed of those, having them move around faster, those weak intermolecular forces are not going to do as much good, and you're going to be able to dissolve less of that molecule in the liquid. How do you feel about that? You guys are super quiet about this. Can I have someone try to summarize what I just said? Who felt? I want to have another voice, and then we can clarify. Echo, would you like to describe that combination, or?
That if the intermolecular forces in the molecule are...
Between the molecule and water.
Yeah, between the molecule and water are stronger, then it's going to be more soluble in water.
Very good way to say it. So the weaker the intermolecular forces, the less there is to kind of hold on to. And so the gases will be less prone to stay soluble. Once those lighter molecules do reach the surface too with any speed, they're likely to not be held to the same standard as the solvent is, and so they'll be able to evaporate and go back to their gas state. So then how do we get carbonation in our soda cans? How do we make so much CO2 dissolve?
Pressure.
Tons of pressure. All right, so let's keep that in mind. Let's think about the pressure over a gas. As we increase the pressure of a gas over the liquid, what happens to solubility? Go ahead and click in your response, and then we'll discuss. Okay, very strong answers on this one as well. Someone like to take a stab and explain this? Go ahead, Aurora.
In the case of the picture, I guess, the smaller the area, the more likely the molecules or particles are likely to hit each other, which increases their speed, which increases their solubility.
Okay, so the speed is one part of it, but another major part is frequency of collision of the gas molecules with the surface of the liquid. And so if we think about increasing of pressure, that means we increase the frequency of collisions and the speed of collisions. So that means we're going to have more frequent gases are going to hit the surface of this, and they're going to be forced into solution. So that's how we bottle. Okay, I think beer might be different because that's actually due to the fermentation. It's actually generated inside. But soda, that's how carbonated water, other things, is you put it under really high pressure of CO2. That forces more to dissolve. You cap it. And as soon as you open it, that's why you hear a psh. It's because now you release that pressure. Some of that CO2 is now released. It tries to equilibrate. It takes a little while for it to get back to equilibrium of how much is supposed to be dissolved. And the soda warms up during the process, which decreases solubility again. So I agree with the majority of class. All right, so in order to have this conversation, we need to think about partial pressures to see how this relates back to our climate on Earth. Partial pressure is a term that I think is really intuitive, but sounds technical. So our atmosphere right now is that if we measure the pressure, it would be 1 atmosphere. What is the partial pressure of carbon dioxide in our atmosphere right now? The atmosphere is composed 20%. What is the partial pressure of oxygen? Let's do that instead. That makes more sense. So oxygen makes up about 20% of all the gas molecules. So what is the partial pressure of oxygen in this room? So if we took away all the nitrogen molecules and just looked at the pressure that comes specifically from O2, it would be 20% of the total pressure. And so if we look at the composition of air in total, most of it's nitrogen molecules, a lot of it's oxygen, and then we have a whole bunch of other stuff. The concentration of CO2 is so small that we refer to it not as percent, which is parts of 100. We refer to it as parts of a million. So we have historically 300 to 350 parts per million of the atmospheric molecules were CO2. Do you guys know how much it is now? It's over 400. It's about 410. And most of that change has occurred since the Industrial Revolution. So we want to think about where does that 400 parts per million, how does that influence the oceans? So let's take a look at, do we need to do this on partial pressure as well? Kind of the same principle we just talked about. If we increase the partial pressure of CO2 over a gas, how will that relate to the amount dissolved in the gas, in the liquid? It's going to be the same exact thing, right? So if we double the partial pressure of the CO2, we're going to get twice as much in solution. So it's not that the total pressure of the Earth is getting greater, but that instead of 300 out of every million molecules being CO2, now it's 400 out of every million molecules are CO2. So that increases the partial pressure of CO2 over the oceans, which means that we dissolve more and more. So solubility of a gas, this is Henry's law. Solubility of a gas is directly proportional to the partial pressure of that gas. Basically saying if we double the partial pressure, we double the amount that dissolves. And there's a constant in there. But didn't we just say that the amount dissolved depends on the temperature? If we warm it up, we're going to have less gases dissolved, right? Where is that in that equation? Or is it in that equation? Does anyone see temperature? What's that? Samantha?
It was KH.
So KH is only specific for a particular temperature. As the temperature goes up, what do you think happens to KH? As the temperature goes up, we know the solubility goes down. Solubility is on this side. So as temperature goes up, this has to go down in order for the solubility to go down as well. You can go ahead and look at a table of KH values of CO2 and water at different temperatures, and you'll see it'll go down and down and down, which means that less and less and less of the gas is going to be soluble. So let's take those factors and let's think about CO2 in the oceans. If we look at CO2, maybe I'll just put these two diagrams up here. Take a minute. Can you guys read those texts? Should I make this a clicker question? You can see it on your screen. You can zoom in. So you should be able to see it on your screens now. Should be able to zoom in to see all the letters. Try to get a feel for what's being shown in these diagrams. So since we're doing this as a clicker question, go ahead and click on the part of the screen that represents our impact on CO2 production. And I advise you to pinch and zoom as much as you can, or zoom in other ways if you have a computer.
What was the question?
Which part of this graph shows humans' impact on CO2 production?
That sounds stupid, but.
Go ahead and tap on your screen. Do you have to hit submit, or you just tap?
You can hit send.
I think you have to hit send, or else I don't see it. Tap on the image and then hit send. It's pretty cool. All right. So, do you guys feel comfortable saying that we make a very small percentage of the change in CO2 concentration throughout the planet? Right? Respiration of all living things, plants and animals, makes up 38% of the natural emissions of CO2. The surface of the oceans. What does that mean? The oceans are a source of CO2? How does that work? Respiration's included in here. That's all marine animals as well.
Underwater volcanoes?
Carbon dioxide is leaving the oceans, especially in like warmer parts of the ocean.
Okay. But it's also going back in. And so this isn't accounting for both directions. This is just saying where is CO2 being produced, not where is CO2 being pulled back in. You see over here on the right side, the ocean is also a sink, which means the 60% that's producing is also being pulled back in. So how would you guys predict that the increasing temperature, climate change means that there's more CO2 in the atmosphere, greenhouse gas means it traps heat, increases the temperature of the planet. How does that influence the solubility of CO2 in the oceans? Go ahead and talk to your neighbor and try to answer this question.
Which is essentially what's happening. That's what I'm saying. Like that. Breaking cycle. Oh yeah.
So let's go one at a time. First part, can I have a volunteer? How does increasing atmospheric CO2 pressure impact solubility? Just that alone. Avery?
That would increase solubility.
That'll increase solubility. What about the increasing ocean temperatures because the climate is warming? How does that influence solubility? Decreases it. So what happens overall? What's the net change? So let's take a look at these two separately. So here's Industrial Revolution was right around 300 parts per million. Now we're over, I think we're at 410 or something like that, parts per million. It's been going up, like I've been watching it the last 5 years, and it's scary how fast it's been going up in the last 5 years. All right, so that's the partial pressure, so that means we're going to increase the amount dissolved. But then the ocean temperatures, if we just look at ocean temperatures as recorded over the last 130 years, ocean temperatures have gone up by a drastic amount. And actually, this isn't even current data. This is 2009, and there's actually been, 17 of the 8 hottest years on record have been the last over the last 18 years. So I want you to go ahead and take a look at this figure. We'll do another, I'll let you guys zoom in on it again. And I want you to gather from this figure what the overall impact of all that CO2 is in the atmosphere. You should be able to zoom in on your screens if you need to.
This is recent changes.
Thank you.
The C is. Back in pre-industrial, it was equilibrium, but now, with recent changes, it's a global warming system. Which is that ginger? It's just now people, I'm looking at this half. Now with this one, with this one it looks like we're not reabsorbing like aside from.
Alright, are you guys ready for cold call on this one? You feel confident in reading figures like this? This would be a great exam question too. Putting something up there like this and having you guys interpret a figure. See some eyes rolling back there? Let's hear from, who wants to go for this one? Let's hear from Manu. How do you interpret all the information that's up here, all this data?
Well, overall, it's saying that the CO2 has increased in parts per million over the years. And
so where is it increased?
On the right side.
Lynn, you want to add to that?
Industrial, particularly. And then, changing land use.
So you're focused on the two arrows on the far left side? Those are drastically increased?
Yeah, and then you also have a change in the absorption.
So if we go back to the last question that I asked, what's the net result of increasing CO2 concentration in the atmosphere, which leads to increased partial pressure of CO2, but increased temperature as well? What part of this graph speaks to that? Which arrow specifically? So the release of CO2 from the ocean and the absorption, the net difference between these two is a net intake into the ocean. So what that says is that these are additional sources being released from us. So a total of 32. 10 of those are being absorbed by the ocean. That's a pretty significant chunk. That's a third of all the CO2 that's being output right now is being taken up by the oceans. What happens when CO2 goes into the ocean? So as we'll talk about later in equilibrium, CO2 dissolves, forms carbonic acid. Carbonic acid releases protons, which makes it acidic, which kills a lot of sea life. It also increases the temperature, which changes the regions in which plant life can survive. A lot of different things are changing.
Death. It's death.
All right. So the last question, last part of this. How does molar mass or molecular weight of a compound increase or decrease? How does that influence the solubility of a gas? Oh, it's you can tap on the part, it's fine. We'll figure it out. All right, a couple more seconds to tap your part of the screen and hit send. All right, closing up. And I can't see what you guys responded. That's useful. All right. Help me out. Can I get a volunteer, a new volunteer? Can I hear from someone in that back corner of the room besides Echo? Riley, you want to share your thoughts on this?
I said that it would decrease
As
the molecular weight increases because it would take more to make that soluble, the molecule soluble.
what do you mean it would take more?
It would take more temperature or pressure.
Okay. Does anyone else want to share their thoughts on which way it would go and why? Aaron?
I said that it would increase because it has an added mass to it, but also, the Van Hoff factor, if you have a really small atom versus a really large atom, they still play the same role in solubility.
Okay, so I think you might be overlapping two concepts. So you might be talking about the colligative properties. And the colligative properties are for something that's non-volatile. And gases by definition are volatile because they go into the atmosphere. So careful on overlapping those two. But I think the first point that you made, where you have more mass. So if we think about what allows a gas to escape, the faster it can go, the more likely it is to leave the liquid, right? If it's heavier, is it going to take more or less energy to get it to go the same speed? More. So the heavier it is, the more energy it needs to go the same speed to overcome gravity and intermolecular forces.
Yes.
And then the second component is, even if they're nonpolar, the larger molecule is, the more opportunities for intermolecular forces it has. So like the reason the geckos stick to walls is not because they have great intermolecular forces, it's because they only have London dispersion forces, but they have so much surface area that the number of places in which they can have a really weak intermolecular force makes it just insanely strong sticking power. Mm-hmm. Same thing is true of a gas. The more opportunity you have for a gas to interact with a solvent, the more likely it is to stay in the solution. So let's take a look at the data. Which one of those is the most soluble and why? So we have solubility over here, all at the same temperature. We see an increasing trend. What about the molar mass?
Also increasing.
Also increasing.
Yes.
All right. So I think I have a table at the very beginning of the worksheet for today saying how does temperature, partial pressure, and molar mass impact solubility. I want you guys to be able to confidently answer that and describe why. All right, part 2. Ready to shift gears? That was a big, strong, confident end to Henry's Law. All right, in this part, I want you guys to be able to identify the reactant and product in a concentration versus time graph. Thanks, Moab. and describe how fast reactions are in relation to the reactants being consumed and the products being formed. If you guys have gotten a chance to already complete activity 36, which is what I think most of you have done, then hopefully this will be a bit of review, and that'll allow us to start activity 37. So let's take a minute and popcorn some ideas. We talk about kinetics, right? Kinetics is not just a chemistry classroom activity. So can I have some volunteers of chemical reactions that we might care about on a regular basis? Yes.
Does medicine have to?
What about medicine?
So like, let's say if you're having a heart attack, you know, like you need your medicine to work quickly to like resolve wherever clot it is.
Yeah. And there's an awesome number of components to that. One of the biggest challenges for people who have stroke is they used to only have warfarin as the drug that they could use. Warfarin gets chewed up, metabolized by our bodies fairly quickly, and the therapeutic dose, so how much you need for it to be effective, versus how much is toxic to you, was a very small difference in concentration. So you have to know the exact kinetics, how quickly our body chews that up, which is not just based on your body weight. It's based on your enzyme activity, a whole bunch of other stuff. So you have to be really careful to give the right dose at the right time interval so that you're always getting up to a concentration that's effective, and then you don't go too high to get toxic and you come down, up and down, and up and down. So that's a really bad drug for that particular thing. There's a lot of newer drugs that don't exactly do the same thing, but they're much higher therapeutic index, which is the window in which you can dose effective versus toxic. Great. Fantastic example. What else? Tyler.
Chemical weathering of materials.
Chemical what?
Weathering of materials.
Yeah. So how long does it take for materials to weather? You can back out the original date of those materials not being weathered. Fantastic. A geologist coming in strong. What other things? Bria?
Is like aerobic respiration considered one? Like if you're exercising, how long it takes for you to like catch your breath or whatever?
There are very many chemical reactions going on there, and so that's a bit difficult to pin down one specific reaction. But there's a tandem number of reactions. Solubility of gases is one of them, right? How quickly it can dissolve. Oxygen can dissolve in our blood. CO2 can come out. A lot of different things. What if we do really poorly on the exam and you're over 21? What might you do after the exam? Or you think you do poorly. You actually did really well. But if you... Say again? Yeah, yoga. This is exactly what I'm talking about. So if you decide to consume alcohol, you might think about how soon can I drive a vehicle and not be in danger to myself or others. And so there's a kinetics curve of that. So you have initial time of consumption. This is absorption, so this is not chemical reaction of concentration going up. But then over time, how quickly does our body clear that out? What's the rule of thumb that everyone says?
Isn't it like 3 to 4 hours, right?
What's that? So 1 drink per hour used to be the rule of thumb. And for those of you who are doing chemical kinetics lab, that is a first order rate of reaction because the concentration doesn't influence how many drinks per hour. It's actually false. There is a lot more variability to people and to saturating the enzymes, a whole bunch of other stuff. But if you only had like 1 drink and you looked at how quickly it eliminated, if the concentration, which is how high up we are, doesn't affect the slope of this graph, which is the rate of consumption, that's first order. If it's second order, it's going to curve a lot more. And there's a whole bunch of other things we'll get into within the next couple of weeks. So just a word of warning, the 1 drink per hour doesn't include high gravity drinks. It's based off of like a Miller Lite. So try not to use that rule of thumb. If you feel any alcohol in your system, don't drive. It's just a bad idea. Ubers are cheap and plentiful. All right, radioactive decay is another one. Fukushima happened a few years ago, right? There was this nuclear power plant that rupture due to tsunami. Chernobyl is an even way worse one. Luckily, Fukushima was contained for the most part, but a lot of it got out into the water. And so you can calculate how long it takes for radioactive material to decay. In Chernobyl, that's thousands of years because they never contained it. In Fukushima, you could still detect it now, depending on where you are. If you're interested in medicine,
I don't think that's a puppy. I don't know what it is.
then a lot of times, I think it's a rat.
Oh!
If you, by the way, we are going to have our seminar series this spring. I hope to start it as soon as possible, but there will be medical researchers as well as clinicians coming on Wednesdays to talk to you guys about what they do, their career path, and also to hear some questions from you. So I'll keep you updated on when that actually goes in place. But for those biomedical researchers, they want to find a new cure for cancer, but first you have to identify where it is. So you have to have some sort of tracer that goes in that's fluorescent or radioactive. This is a fluorescent dye that goes into the animal. It gets absorbed specifically at the site of, I think this is a tumor, I think this is its liver. And then you can image that with fluorescence. So there's a number of different factors that are all kinetic reactions. Whether you can then look at whether you inject it into the vein or into a muscle, seeing how that distributes throughout the body. Those are all kinetic processes. All right. So a lot of different things in which kinetics does play a role. So for this class, we're going to be talking a bit more about pollution and some chemical reactions that are involved with smog. That's how we're going to start out the semester. So on your guys' worksheet, I think that there are two graphs that show concentration versus time of reactants and products, A and B. Do you see those? This is still on your worksheet from today, not in-class worksheet. You didn't pick them up? Okay. Fair enough. So I want to talk about two things. I want you to identify what the kinetic phase of a reaction is and the equilibrium phase of a reaction. Go ahead and look at those two graphs. Look at which part might be described by kinetics, your understanding of that so far, and what part is described by equilibrium.
Are you?
Me showing my dimples is not necessarily mean that I saw
I think it's shared.
All right. What does kinetics mean? What is that word in general? Kinesiology, number of different things. Movement, okay? So what part of those two graphs do you guys identify as being the kinetic phase? Looks like graph 1.
graph.
The one on the left.
Yes.
What part of that is the kinetic phase of that reaction? Colin?
Basically like 0 to around 60 seconds as they're both like curving still. Things are happening and they even out eventually.
Okay, at what point do they even out? Okay, so maybe 80 seconds on that one. What about graph 2? What part of that graph would you consider the kinetic phase and what part is the equilibrium phase? Josh?
0 to about 60.
Which one is that?
That's the kinetic phase from 0 to 60, and then the equilibrium phase from 60 beyond.
Great. So a reaction like this may be a little bit more complicated. We have A reacting with B forming C, so we have two reactants and one product. Does it make sense that the red and the blue line are both going down? Why? Why would the red and the blue lines be going down over the course of this reaction, Carol?
Because they're reactants and they're being consumed.
Fantastic. So over the course of time, we start with reactants. We know that we start with them because we have non-zero concentrations. Do we have any products at the beginning of this reaction? 0, it's down here, right? And then over the course of time, these two are combining. We're making this. It is increasing over time. and then we get to a phase of the reaction now where no more change in concentration is happening. Does that mean the reaction is not happening anymore? All right, we'll get into that. So we have the kinetic phase on the left, equilibrium phase on the right. For those who like to talk about Gibbs free energy, the left side is where you have Gibbs free energy is not equal to 0, and the right side, the graph, is where you have Gibbs free energy. Gibbs free energy is equal to 0, not equal to 0, equal to 0. It's written up here. I'm just turning myself around. We'll be spending a lot of time this semester describing how Gibbs free energy describes where the reaction is, if we're at equilibrium or not. All right. If we're talking about kinetics, we can talk about smog. Does anyone know what city this is? Salt Lake City. So Salt Lake City on a clear day looks like the right, and on a non-clear day looks like the left. I can attest to this. I've driven through there. I've flown in, and it's crazy, this blanket of smog that sits over the city. The reason is because it's in a bowl. And so when smog is generated in the city, unless there's a wind blowing, it just settles in the city, and it's really unpleasant. So that reaction happens when you have the combustion of gasoline, impurities in gasoline, and you bring in nitrogen from the air. So these are some of the impurities in photochemical smog. If you look over the course of a day, 4 a.m. to 4 p.m., you see concentrations changing throughout the day. Why is that?
Because people driving more cars.
So rush hour in the morning. In the afternoon, you have more of a mixed rush hour, people leaving at different times, maybe. And then after 4 o'clock, you're probably going to see a little bit of a spike there as well. So what I want us thinking about is one very specific reaction in the smog formation process. I want you to look at this graph and try to identify which one of those lines represents the formation of NO2, if that's the reaction that's happening. Let's do a couple more seconds. If you've already got that, then go ahead and try to identify the other two lines. David, would you mind describing which one you think might be the formation of NO2 and why?
I believe it's C because that's what's being created.
Okay, so if we have a chemical reaction written in this direction, then we assume that there's very little products starting and that they're forming over time. We notice that only one of these is forming over time, that we're increasing. Okay, there's some nuances we're going to add to that in a second here as well. I want you to go ahead and say which one of these would represent the consumption of O2. Two is really important.
Well, I had said it should be 1/2, and then she like corrected me to the wrong answer.
All right, you guys are not in agreement. Find someone who disagrees. Convince them why your answer is right. How do you know which one's being consumed quicker or not quicker?
It is a combination.
Sounds reasonable. All right. We have a 2-to-1 set of responses. I want to hear from Lauren what your group discussed and which one you think might be representing O2.
Okay, I said B.
Why?
Because I thought that A was the two NO molecules because it's got a higher concentration.
So what's their initial concentration? Is it different between our two reactants? Okay, so on this graph, the starting concentration is these two. So what's the difference between those two then? You want to pass? Okay, Jason?
I said A was O2 because it's the NO is getting consumed twice as fast than the O2.
Okay, so first of all, why do you say that just based on the equation?
Because it takes two NOs and one O2 to form two NO2s.
So in the same time frame, you would consume one O2 and two NOs, so we know that NO gets consumed twice as fast.
Yep.
And then on the graph, how did you match that?
If you look at where it ended at, it's like 62 there, and then drop down to B, it's at like 31 or so.
Okay, so over the course of the reaction, we're consuming more of one of the two. And we know we're consuming, by the way, because both of the concentrations are going down. So going back to the initial question I asked David, he said one of them is going up. It's also a little more nuanced because there's one going in one direction, two going the other, and based on a reaction, I could have tricked you and flipped this, right? And then you would have had one going down and two going up and said, oh, it's a reaction going in reverse. But that wouldn't be mean. So instead of looking, as well as looking at the beginning and the end of the reaction, how else can we look at this and say that A is getting consumed less quickly? What about the graph can we use to say A is being consumed less quickly? Ruby?
The concentration changes less in the same amount of time.
Okay, and graphically, how might we describe that?
In 8,000 seconds.
So not over the entire course, something more specific. Colin?
The slope?
The average rate.
So we could say the average or the instantaneous rate of change of concentration. So the slope of the graph represents the rate of change of the reaction. You guys did a lot of stuff with that in your POGO activity 36. This is graphically what that looks like. So the slope of the graph of B is always going to be twice as steep as the slope of the graph of A. Regardless of how much, you don't have to start with the same amount for that to be true. You have to consume two NOs to consume one O2, so the slope is always going to be twice as steep. How should that compare to the slope of C? How does the slope of C compare to the slope of A? It should still be a twofold factor, but it's not just a twofold factor. What's different as well?
One is going to be positive.
One's negative, one's positive. So the slope of B and C should be the same at any point in time, but the opposite of each other. All right, so I want you thinking about the reaction, the stoichiometric coefficients, and how that allows us to predict which reactant is which product is which line, and this is something I will ask you on an exam, is to look at a graph like this, identify which is a reactant, which is a product, specifically which reactant and which product.
Is it on an exam or a B exam?
On Wednesday. All right. So in the last 6 minutes of class, we are going to start on activity 37. And activity 37 is going to be our supplemental instruction for the week. So whatever you don't finish today, we will work on in supplemental instruction. You'll turn in on Monday. So that's good news. We don't have an additional activity for you guys. The other good news is there is no homework this week. There's no free quiz for Wednesday. There is no homework for Sunday. There's no post quiz on Monday. Because you have a test. Alright, so take advantage of these next 5 minutes to get started on activity 37. Read very carefully.
Okay, we're gonna go, I'm sorry.
Alright, we'll be helping you walk around. Still 3 minutes left in class, guys. No getting up and out unless you have somewhere you have to be, like a normal class, please. I'll think about it. I'm going to try to walk around and keep people going with activities. So try. Does anyone not have activity 37, by the way? I have a few extra copies of activity 37. Anyone else in activity 37?
It's time to roll out.
Alright guys, so as you're heading out, activity 37 content is not in the exam activity 36. Just to be clear and answer some questions I had, activity 37 will not be on the exam, but activity 36 in today's class will be. So supplemental instruction will start where we left off in activity 37, that will be complete, you'll hand that in. If you don't, come to supplemental instruction on Monday.
Well,